We have seen this simple DC or direct current circuit in previous slides. It shows a battery supplying direct voltage and current to a circuit. Remember that direct current always flows one way around a circuit, from positive to negative. Let's for a moment imagine that instead of the battery being fixed in place, we could spin the battery round and around, reversing the polarity of the voltage applied to the circuit, first one way and then the other. As we did so, the current flowing in the circuit would also keep flipping around, first in one direction and then the other. We call this continuous reversal of the supply voltage polarity and the constant reversal of the current flow an alternating current. Alternating currents are very useful to us in many ways. They make the general distribution of electrical power much easier than it would be if it were DC, and we can easily convert one AC voltage to another using devices called transformers. This is a symbol for an AC voltage or current supply source, and we will see an example of one in the next slide. Alternating current can be generated in a number of ways, but the one you may be most familiar with is the AC generator or alternator. The power to our homes is generated by AC alternators in power stations, and we use one in our cars to charge the battery. A basic alternator uses a powerful spinning magnet that sits within two coils of wire. You may remember seeing a demonstration of one in your school science lessons. As the magnet spins, the magnetic field induces a current flow in the wire coils above and below it. When the north pole of the magnet is at the top, the current flows in one direction, and when the south pole is at the top, the current flow flips around and flows in the other direction. The current induced in the coils is at its maximum when the poles of the magnets are closest to the coils and at a minimum when they are furthest away. We can draw a chart of the current flowing in the circuit attached to the coils, which shows the strength of the current and when it changes direction with the spin of the magnet. As the north pole of the magnet spins towards the top coil, the current flows in one direction, starting from zero and reaching a maximum as the magnet pole passes under the coil, and falling to zero again as it moves away. As the south pole spins towards the top and the magnetic field is reversed, the current flows in the other direction, reaching a maximum when the south pole is under the coil and falling away to zero again as the pole moves away. One full rotation of the magnet causes one full cycle of the current wave. The half-cycle current flow in one direction is showing going upwards from the 0 point on the graph, while the opposite half-cycle, when the current is flowing in the opposite direction, is showing going downwards from the 0 point on the graph. The horizontal line going from left to right in the center of the graph is the timeline recording each interval of time where we have taken a measurement of the current flow. Our chart or graph shows the current flowing in one direction, then reversing and flowing in the other direction. However, the shape of the graph will be the same no matter whether we are measuring the current or voltage flow in the circuit, and you will come across graphs like this in your studies that may represent either. Let's now look at some of the terms we use to define and measure an alternating wave. We have the maximum value that a voltage or current will reach at the very peak of the wave. We call this value the peak amplitude. It has both a positive peak value and a negative peak value, as a voltage or current changes polarity or direction in the circuit. It has the time taken for the wave to complete one full cycle in seconds or in fractions of a second. We call this the period. The alternating wave in this example takes 1 second to complete one full cycle. The wave in this example on the right shows an alternating wave that has completed 2 full cycles in 1 second. We say the wave has a frequency, which just means how frequently each wave occurs in 1 second. This is important for us to know, as radio waves alternate at a frequency of many thousands or even many millions of times each second. We give frequency the small letter f when we need to show its value. Frequency is measured in Hertz, in honor of the German scientist, who confirmed the existence of electromagnetic waves. Our first example has a frequency of 1 Hertz, which we shorten to Hz. Our second example has a frequency of 2 Hertz, or 2 cycles per second. The shape of this wave is common in nature as it describes many forms of natural vibrations. It is called a sine wave, after the mathematical formula that describes its variations. We now need to look at a property of an alternating wave called wavelength. Wavelength applies only when the vibrations resulting from an alternating wave begin to travel through a medium, like air or a wire conductor. Sound waves are a good way to learn about wavelength as they are easy to visualize. This is a loudspeaker in an audio system. It turns an alternating electrical current into mechanical vibrations that we can hear. We will connect an amplifier, generate an alternating audio waveform to the loudspeaker with a frequency of 1000 Hertz. The 1000 Hertz signal causes the loudspeaker to vibrate forwards and backwards in time with the peaks in the 1000 Hertz audio signal. Pressure waves from the loudspeaker cone travel outwards from the loudspeaker at the speed of sound. 1 pressure wave for each peak in the signal, one after the other. We call this propagation, and that term is used whenever a wave travels outwards from a radiating source, be it a sound wave, a ripple in a pond, or an electromagnetic wave from our transmitter. The speed of sound in air is around 343 meters per second. We can see that the 1000 Hertz wave is stretched out, with each cycle of the wave having a fixed distance between one ripple in the air it creates and the next one. If we know how many times each second a loudspeaker is vibrating, which will be the frequency of the audio signal in cycles per second, and we know how fast in meters per second each wave peak is travelling, we can calculate the distance between them simply by dividing the frequency into the speed of sound. We call this distance the wavelength, and for any frequency it will depend on the speed of propagation. This will begin to make more sense when we start to look at how electromagnetic waves propagate from the antenna, which is connected to our transmitter. They propagate at the speed of light, and we will see that in a later session. Unlike sound waves, which are pressure waves in the air, electromagnetic, or EM waves for short, are a form of pure energy. EM waves travel through the vacuum of space at the speed of light. The EM wave, as its name suggests, is actually 2 waves which are bound together. There is an electric field and an accompanying magnetic field. The 2 waves exist in perfect synchronization, the waves rising and falling in amplitude together. The EM wave has an electric field and a magnetic field which are rotated 90 degrees apart. If one wave is horizontal, the other will be vertical. We call this difference in field direction polarization, and it's very important in determining how we design our antennas. When we talk about a radio or EM wave, we refer to the electric field when we use the term polarization. We will see later, when we talk about antennas, why knowing the direction of polarization of the EM wave is so important, whether we lay our antenna horizontally or vertically, for example. EM waves travel at the speed of light, which is 300 million meters per second. The frequency of the EM waves we use in amateur radio is very high indeed, thousands, millions, or billions of cycles per second, or Hertz. We need a way to handle such large numbers, which we shall look at in the next slide. During this foundation course, we will be dealing with EM waves that have frequencies that are measured in the thousands, millions, or even billions of Hertz. To make our calculations easier, and to make the numbers easy to understand, we use a system of multipliers. Multipliers are shown as letters placed after the frequency value, to tell us if we are dealing with thousands, millions, or billions of Hertz. A small letter K standing for kilo means we must multiply the written value by 1000. The capital letter M for mega is used to show the number is to be multiplied by 1 million. And the capital letter G for giga is used to tell us to multiply the number by 1 billion. 1 kilohertz, or kHz, is 1000 Hertz. 1 megahertz, or MHz, is 1 million Hertz. And 1 gigahertz, or GHz, is 1 billion Hertz, or 1 followed by 9 noughts. As we learn more about EM waves, we will need to work out the length of the wave as it propagates between a transmitter and a receiver. Remember, the letters EM just stand for electromagnetic. If we know the frequency in Hertz of any EM wave, and we know the speed of propagation of the wave, in this case the speed of light, we can work out the length of the wave in meters, called the wavelength. Knowing the wavelength of an EM wave is very important when we come to building and connecting an antenna to our transmitter or receiver. The length of the antenna has to be cut accurately for the EM wave we intend to use. To express wavelength, we use the Greek letter lambda, which is like the letter Y upside down. We measure wavelength in meters, or if the frequency is very high, sometimes in centimeters. Wavelength in meters is simply the speed of light divided by the frequency in Hertz. The speed of light is 300 million meters per second. All we need to do is divide it by the frequency. Let us try to find a wavelength for the 14 MHz amateur band. Here we are dividing 300 million by 14 million Hertz. This is the speed of light divided by the frequency in Hertz. We've got some very big numbers here, but there is a trick we can play with the division. We can cancel out some of the noughts on the top line and the bottom line, and here we've cancelled out the 6 zeros that represent the millions on both sides of the division. Don't worry if you've not come across this before. You can use the full number if you want. This just makes it easier. We are left with 300 divided by 14, which equals 21.4 meters, or thereabouts. Since the band covers a range of frequencies, we round the number to 20 meters. 14 MHz is commonly referred to as the 20-meter amateur band. You'll find it easier to remember this calculation if you divide both numbers by 1 million. So while this calculation is correct, this is a much easier number to remember. Wavelength is 300 divided by the frequency in megahertz. To help you with your conversions of frequency and wavelength, you will be given a lookup table on page 4 of the Foundation License Examination Reference Book. This will be given to you during the exam. To look up a frequency of, for example, 14 MHz and find the wavelength, we locate 14 MHz on the horizontal scale at the bottom of the chart. Note, the scale is not linear. The numbers bunch up as they get larger, and you may need to estimate the actual value on the scale. Draw a vertical line from the 14 MHz value on the lower scale until it meets the diagonal line on the table. Then project that point on the diagonal line in a horizontal direction to the wavelength scale on the left. Read off the appropriate value in meters for the wavelength you are trying to find, or vice versa. Remember, the scale is not linear. We call this scale a logarithmic scale, but you will not need to know this for the exam. Just allow for it when you estimate the exact scale for the value you are trying to convert. You will see on pages 7 and 8 of the Foundation License Handbook information on frequency and wavelength. There are many different frequencies and wavelengths allocated to amateur radio in the RF spectrum. At the extreme ends of the spectrum, at the very low frequencies and at the super high frequencies, the equipment and operating techniques become very specialized. We divide the spectrum up into frequency bands and assign them names. For example, low frequency, medium frequency and high frequency bands. And these are heavily influenced by solar radiation from the sun and enable intercontinental communication. From 30 MHz to 300 MHz, we have the very high frequency bands, or VHF bands. The 50 MHz, 6 metre, 70 MHz, 4 metre, and 144 MHz, 2 metre amateur bands fall into this frequency range. From 300 MHz to 3000 MHz, or 3 GHz, we have the ultra high frequency bands. The 430 MHz, 70 cm, 1.3 GHz, 23 cm, and 2.3 GHz, 13 cm amateur bands are all in this band. But we tend to refer to any frequency over 1 GHz as microwaves. VHF and UHF frequencies are popular for local communication and are typically called line-of-sight communication. Wavelengths in this frequency range are easily blocked by buildings, hills, and other structures, and are also limited by the curvature of the Earth. Above 3 GHz, we have the super high frequency, microwave and terahertz bands. These are highly specialized areas of experimentation and operation. VHF, UHF, and SHF frequencies are mainly affected by atmospheric conditions. Air temperature and pressure, moisture content and rain can all increase or decrease the distances the waves travel. We really appreciate you taking the time to watch this video. Don't forget to check the video description where you'll find additional information about the video you've just watched, along with links to products used and to the Hadai's website. If you enjoyed this presentation, please feel free to hit that like button. Maybe you'd also consider subscribing and clicking the notification bell so we can let you know the next time we release another video. Thanks again for watching.